Okay. Oh, that's not going to work. So this is a review slide, which works fine for us. Okay, so we already covered this one on Friday. But I just wanted to kind of remind you what it means when we talk about precision and accuracy. So precision is scatter, okay? So in the case of, if we call this A, B, and C, okay, in the case of A, we have a lot of scatter, poor precision, and actually the average of those is not on the bullseye, so the accuracy stinks too. B, they're nice and tight, so we have good precision, but poor accuracy. And C, we have good precision and no lack of scatter, and it's the bullseye, so it's accurate. So we have both. Okay, and this actually is a review slide too. So whenever you're doing analysis, you may have heard of the term error and uncertainty. And error means how close or how far away from the real value you are, your accuracy. So error is associated with accuracy. Uncertainty is associated with scatter. Okay. Yeah. So just to kind of remind you. So uncertainty is associated with precision. Now this is a new slide. If you've had well, you've had chemistry before, but if you've had an instructor that has emphasized rounding to the correct number of significant figures, here's where you roll your eyes, okay? But aside from rounding a calculated number, whenever you report a measured quantity, so I brought this in so we could like measure volume with this, right? Whenever we report a quantity such as volume, we automatically, when you write it down in your notebook or in your report or whatever, you automatically relay the number of significant figures that's showing the correct amount of uncertainty. So for instance, and we're going to kind of get into this, but if I had scale A, scale B, and scale C, and let's just say scale A weighs 1.1 grams. That's what I would report it down to. Let's say scale B weighs 1.13 grams. Okay, costs more. That scale B would cost more. And let's say I have another scale that weighs out to the nearest 1,000th of a gram. Okay. So the significant figures here, and we'll talk about counting significant figures, but actually I have 2 sig figs there, 3 non-zero digits there in B, and I have 4 non-zero digits here in C. Okay, C has more significant figures, and honestly, this value has less uncertainty in it, okay, than the other values. So significant figures can do that for you. Anytime you measure something, whether it's volume or mass or anything, there's always a little bit of play in it. Okay, there's always a little bit of play in it. And actually, yeah, I guess that's all what I want to say. Okay, so when you report something that has a measured quantity that has uncertainty in it, like volume or mass, okay, from left to right, the rightmost digit is where the uncertainty lies. So for instance, kind of the convention is like this. If we look at the examples a minute ago, like 1.1 grams, okay? The uncertainty lies in this tenths place, okay? 1.13 grams. The uncertainty, and I'll put a question mark over the hundredths place. That's where the uncertainty lies, okay? Here, 1.132 grams. Okay, the uncertainty lies in that last digit. Okay, put another way, the digits I'm circling are totally certain. Okay, so those are totally certain. Uncertainty in the rightmost digit. So kind of the opposite in a way of quantities that have uncertainty in them, measured quantities with uncertainty in them, are exact numbers. So there's no play in these numbers. Okay, so exact numbers, there's two types of exact numbers. One is by counting, an exact number by counting. So if I count people, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, there are 9 people in this room. I wouldn't say there are 9 plus or minus 1 people in this room. Okay, not the way I counted it anyway. Right, so that's by counting. The other one is if it's exact by definition. A good example of by definition is this, like, I think we covered remember there's 4 metric prefixes you're supposed to memorize. 1 liter is exactly equal to 1,000 milliliters. That is by definition. All of the metric stuff is by definition. Okay, and the other thing, or another equality, with not in the metric system, but equality I need you to remember or memorize, is 1 inch is exactly equal to how many centimeters? 2.54, very good. And that is exact by definition. Exact. Okay, 2.54, very good. So exact numbers, there's no play in them. So that's actually important to know. If I'm using an exact quantity in a calculation, okay, that exact quantity introduces no uncertainty. Okay. So that will come up later. All right. So let's count those sig figs. So we've already have an example of counting sig figs. So the 1.1, there's 2 sig figs, 1.12, or whatever, there's 3 sig figs, etc. So if you have a measured quantity or a quantity you know that has uncertainty in it, if all the digits are not 0, then they all count. Okay? So you just count non-zero digits. The zeros is what throws us off. Let's say you have a 0, but it's sitting smack dab between 2 non-zero digits. It is significant too. You'll kind of see when I count significant figures, I put a check mark over everything that's significant, okay? Again, it's with the zeros. If you have zeros that are trailing after the decimal place, they are significant. Let me show you an example of that. So trailing means kind of to the right, right? So here's an example of that third rule. Say you had 305.100. So let's put check marks over what's significant. According to Rule 1, those are significant, right? According to Rule 2, that 0 is significant. And this third rule says these are trailing zeros. Those are what we call trailing zeros after the decimal. Those are also significant. Okay? So I'm looking at what? 6 significant digits. Notice I use the word digit, so significant figures and significant digits are the same. Okay. So zeros are what kind of throws us off. If they are leading zeros, they aren't significant. Leading zeros only work for small numbers. So for instance, here's an example of leading zeros. So it's 0.000. Those are 3 leading zeros. I'll put 5, 2, 1. Okay. So they're placeholders. They're important, but they're not significant. And I'll try to kind of show you how they don't add to the overall uncertainty. So let's go ahead and do check marks above the non-zero digits. So we have 3 significant figures according to rule number 1. And according to this latest rule, I'm going to put X's over those leading zeros. Okay. It's about the zeros. There's one more type of zero we haven't talked about, and actually I'm going to talk a little more about that later. But if you have a big number, and it kind of peters off in zeros, and you didn't hardcore put the decimal there. So it looks like this. Let's see. 15,320,000. Okay? So notice if I was going to put check marks, definitely would check the 1, the 5, the non-zero digits. I got 4 non-zero digits. Those last 4 zeros are trailing zeros before an implied decimal. If I were to ask you guys, I bet you would tell me the decimal is right there, right? But it's implied because no one really put it there. So what you'll see me do is put a dash, 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 dash around it. I put it there because it's implied. In that case, if you're familiar with the word ambiguous, if somebody's being ambiguous, they're being wishy-washy. Ambiguity means, you know, it could go either way. So it's ambiguous. We don't know if the uncertainty starts, for instance, clear back here in the ones place. Okay, we don't know if that's the only uncertainty, that's where the uncertainty begins, and those others are known, or does the uncertainty begin here, or here, or here? And in just a minute, I'm going to show you if you have a large number like this with trailing zeros before an implied decimal, there's a way to clean it up with scientific notation. We'll do that here in a minute. Okay, so let's see how we do. Assuming there's uncertainty in each one of these numbers, it's not counted, nor is it by definition. Okay, this first one. I want you, if you would, to just hold up your fingers how many sig figs there are. I'm liking it. Very good, 4 sig figs. How about this one? 5. Does everybody buy that? Very good. 5 sig figs, perfect. All right, this one. I'm seeing some 3s. It is 3. It is 3. Why is this 0 significant? Which rule is that from the previous? It's following. It's a It's a trailing 0 after the decimal. Exactly. So there's 3 sig figs. Let's see. Here's another one for you. How many sig figs? Guess you can do this all in one hand still. 5. Yep, 5 sig figs. Perfect. And how about this one? Why is there only 2? Why aren't these others significant? Because they're placeholders. Exactly. That's how I think of it. Exactly. 2 sig figs there. Good job. Okay. So I'm going to kind of talk you through why you have 2 sig figs, 3 sig figs, and 4 sig figs in those quantities. Okay, the uncertainty starts right here in the tenths place for this one, the hundredths place for this one, and the thousandths place for this one. Okay. So if you have quantities like that, a lot of times they will say that the uncertainty is plus or minus whatever where the uncertainty begins, plus or minus 1, units of whatever that last number digit is, okay? So we kind of have this going on, okay? Plus or minus 0.1, plus or minus 0.01, plus or minus 0.001. Where's the uncertainty lies? Well, if we want to look at, relatively speaking, what we have going on in each one of those measurements, we can come up with the relative uncertainty by taking that uncertainty you saw on the previous slide and dividing it by the best value. So here's what it looks like, for instance, for the first one. The uncertainty plus or minus 1 divided by 2.5. You divide that out and you get 1 part per 25. The next one, the uncertainty 0.01 divided by 2.50. You divide that out and you get 1 in 250 parts. This one, the uncertainty 0.001 divided by 2.500. Then in terms of a fraction, that is 1 in 250. 1 in 2,500 parts. Okay, that's the uncertainty, relative uncertainty. In terms, I think I already mentioned this, in terms of a measuring device that would measure this, this would cost some money, this would cost more money. and this would cost the most money. Precision is not free. Accuracy might be, okay? So let's look at those placeholder zeros, those leading zeros. Why do we put X's over those for small numbers, those placeholder zeros? They're important, by golly. If you don't include them, then it's not the same number. They just give magnitude, okay? So they are very important. Leading zeros and trailing zeros before an implied decimal are very important. But I'll kind of show you that how that works out with regard to relative uncertainty. So for instance, each one of these, 25 or 2.5 or 0.25 or 0.025, 0.00025, we would only get to click 2 significant digits in each case. Okay, starting with these last two. Okay, these last two have zeros that are simply placeholders. Okay, they're leading zeros. So if you were to kind of do the exercise like I did just a few slides ago with the relative uncertainty, okay, you would come up with the fact that in each one of these, they have relative uncertainty of 1 in 25 parts. 1 in 25 parts for all of them. Okay, so they all have the same relative uncertainty. They all have 2 sig figs. So let's return to that last rule. Okay, if you have, he made it. If you have trailing zeros before an implied decimal. There's no decimal up there after that third zero is there. Okay, so again, my kind of convention to show an implied decimal is I put the decimal point, okay, and then I put kind of dots around it. That's my implied decimal. So you know you have at least 2 significant figures because kind of going from left to right, you have 2 non-zero digits. But you don't know if you have really 3 sig figs, 4 sig figs, or 5 sig figs. So it's becoming somewhat of an accepted convention that if the decimal place is shown in a number that would otherwise be ambiguous, that all of those trailing zeros, okay, are significant. So let me go ahead and give you a name for that. So, can't remember, is it like 1, 2, 3? Okay, there is our ambiguous number. And let me go ahead like it's stating, and I am going to show the decimal. There we go. My decimals I show don't have any dots around them. This actually is an explicit decimal. Explicit. If you're kind of saying what is explicit compared to, explicit is compared to implied. So this is an explicit decimal. If you do that, then by golly, what you're saying, I usually think you cared enough to go ahead and put that. If it is explicitly put there, then these count. That's to say, those zeros before that explicit decimal count. So there are 5 sig figs there. Okay. Any questions about that? Okay. So one other thing you can do is to pack up a number in scientific notation. Now, I'm just kind of assuming that we're all good with scientific notation. If you have any questions, kind of let me know. Or I do think that there's some math primers in the back of your Petrucci textbook. So if you have a number packed up in scientific notation, and my slide doesn't say this, you count sig figs in the coefficient. Count sig figs in coefficient. And if you remember scientific notation, when a number is packed up in scientific notation, that decimal number is the coefficient. Okay. So here we have a number in scientific notation, 3.2 times 10 raised to the 4th power. Of course, we could bless you. We could unpack that. We could unpack that, and it would look like this, right? 3.2, 1, 2, 3, 4. Okay, because we have to move it over 4 places. And backfill those zeros. So really, we are looking at 32000. That's the value of the number we're looking at. Okay, but it's 2 significant figures because there are 2 significant figures in the coefficient. Awesome. Well, if you wanted to take that same number and show 3 significant figures, you could do that simply by adding a 0 to the coefficient. So 3.20 times 10 to the 4th is the same number, but now wrapped up in the coefficient, you have 3 significant figures. Because we talked about non-zero, non-zero, and this one is significant because it's a trailing 0 after the decimal. Same idea with 4 sig figs. This gets a little odd. And 5 sig figs. That last one's kind of my favorite. 3.2000 times 10 to the 4th. You're like, really? Any questions about all that? Cool. Very good. So what this slide says is if you just would have the 32000 and the decimal is, remember my convention, if I put dot, 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 dot around it, that means it's implied. If the decimal is implied, then those are not significant. So you would actually call that 2 significant figures. That's what the slide is saying. Yeah, I think it's a pretty good convention. Okay. I wasn't sure if we were going to get to the end, but we might. So in case we don't get to the end of part 2, I wanted to pull these up and make sure you guys would do them for Wednesday. Let's take a quick look at these 2. So these will be due for Wednesday. Now, Petrucci, I think I mentioned this when we went over the syllabus. He does not have answers in the back of the book to the odd or the even problems. But under Doc Sharing, the eCompanion class, or eCompanion website for this class, I went ahead and posted his chapter 1 odd problems. So this is to say, this one is in the back of your book, the 119. So let's see if this works. A little rusty at this. I think that's... So these are screenshots of the problems that are due for Wednesday. The first one, number 19, express the following to 4 significant figures. We didn't talk about rounding. I think that's one of the things I just kind of also, oh darn it, assume that you have. Come back here. But rounding, if the next digit is a 5 or above, you round up. If it's a 4 or less, you leave the number the same. It's probably what you're kind of familiar with. Okay, so for instance, if we take the first one, for example, and we want to take 3984.6, round it to 4 sig figs, we go from left to right. Okay, looks like we're going to truncate it there. Okay, and since this is a 6, what are we going to do with this 4? Exactly. So your answer is 3985. You got it. That's pretty good. Number 20, it's kind of like we've been talking about, how many significant figures in each one of those numbers. So feel free to write them out and put little check marks above them. It might even help, because by the time, for instance, if you're putting check marks above 2 non-zero digits, and a 0 in between, you're like, oh my gosh, well that must be significant too. Okay, so check marks would be fine. Okay, on to the next topic. So we talked about significant figures, okay? Now, when you do calculations with measured quantities that have uncertainty in them, you have to round your answer correctly. And that's exactly what we're going to talk about next. Okay, calculation with measured quantities in which there is uncertainty. And it's broken up into mathematical operations. Addition and subtraction is the same rule. Okay, we're going to talk about that first. And then multiplication and division is a different rule for rounding. We do a heck of a lot of more multiplying and dividing in chemistry than we do adding and subtracting. But we do a little bit of adding and subtracting. So if you have two quantities and there's uncertainty in them, and you're either adding or subtracting those two quantities, you go ahead and let your calculator do the grunt work or whatever, and then you round it according to the fewest decimals of all of the things that you're adding and subtracting. Fewest decimals. Okay. So I'm going to kind of talk you through how I love this. There's actually a course in courses, I'm sure, in how uncertainty propagates through either your experiment or your calculations. Uncertainty, it's kind of insidious. So I'm going to show you how uncertainty propagates if you have volumes, two volumes that were measured with different equipment. And so we've been talking that in the first volume, the uncertainty begins right here. Okay, in the other volume, the uncertainty begins right here. And you're supposed to add those together. So you would line them up on the decimal. Okay, the red number is where the uncertainty begins. Okay, so you basically have uncertainty in two different locations. Lining them up on the decimal, bringing them down. Anything that is added to a red number is contaminated red, okay? So basically you end up with 29 point red hot 642, okay? You can only have one uncertain digit. So we have to lop it off right here, don't we? Which, by the way, is the fewest number of decimals in the things that we were adding. Let me go ahead and take a look up there. The two things we're adding, okay, can you see where we have 3 decimals here and we have 1 decimal here? So according to the rule I just gave you, you have to round according to 1 decimal, and that is exactly how you round. Okay, so that's kind of how it works. So your answer would be 29.6 milliliters. That's just kind of showing you the behind the scenes why it does that. Okay, so adding and subtracting, fewest decimals. Multiplying and dividing, it's the other rule. Multiplying and dividing, you look at all the stuff you multiplied and all the stuff you divided, you count significant figures in each term, and then you round to the fewest. Okay, so it's always fewest. Okay, with multiplication and division, it's sig figs. With addition and subtraction, it's decimals. All right, so let's see how that propagates through. Let's say you had the two dimensions of a rectangle, and you were supposed to calculate area. So, of course, area is length times width, so we're going to multiply 12.34 centimeters by 1.1 centimeters. Okay, so the uncertainty, though, begins right here in the 12.34 centimeters. The uncertainty begins here in the 1.1 centimeters. Before I go on to show you how the uncertainty propagates through, can you see where, or here, just hold up your fingers, sig figs. Okay, how many sig figs are in this number? I'm liking it. Perfect. Same thing. How many sig figs are here in this number? 2. Perfect. So according to the rule I showed you, you have to round according to 2 sig figs. I know it's tempting to give more digits than that, but you start from left to right, take your first 2 sig figs. Okay? That's it. But this is how it propagates through. And if you're like me, I don't do a lot of longhand multiplication. Here's the 2 numbers that need to be multiplied by each other. There's the red hot number. But we're going to take the bottom number and we're going to multiply it by the top number, like the bottom number in the ones place. Okay? Write it down. And then, oh, wait a minute, I said that wrong. See, it's been too long. Okay, it looks like we're taking this number and multiplying it through. Okay, and then we're moving it over one lane. Okay, and then we're taking this number and multiplying it through to get this, and moving it over a lane. So then when you bring down the stuff, making sure what's red stays red at the bottom, you end up with 13574. You see that you have 3 decimals from the end to put your decimal place, right? You can only keep one red hot number, okay? So that means you got to truncate the darn thing right here, okay? And then how many sig figs is that? That's 2, yeah. But here's a little bit of the catch. Since this is a 5, what are we going to do with the 3? Round it up, exactly. So your answer is going to be 14 centimeters squared. So I say we, but you're going to get some practice at working problems and rounding them correctly. And I'm going to be a stickler when you hand them in for your homework so that you can get it perfect for your test. How's that? Not bad. Okay, so just to kind of summarize, there's kind of addition and subtraction, multiplication and division go together. Okay. If you are adding or subtracting, you round according to decimals. If you're multiplying or dividing, you round according to sig figs. That's it. Sounds like it should go on your refrigerator. So we did definitely get through. Anyway. But keep this in mind. If you're using, if in your problem you're using like the whole 1 kilometer is equal to like 1,000 meters, if that's somewhere, remember kilometers and meters, that's by definition. Okay? If you're using the 1 inch is exactly equal to 2.54 centimeters anywhere in your calculation, it brings no uncertainty to your calculation. So you don't count that when you're counting decimals or sig figs. So there we go. Wow. So I guess you're going to get to do 21, 22, 23, and 24. Remember the answers to 21 and 23 are under doc sharing. So let's take a look at those right quick. If I can find it. Okay, so 21 and 22 look like this. Perform the following calculations. Express each answer in exponential, that's scientific notation, with the appropriate number of significant figures. Okay, it looks like the first 2, A and B, are both multiplication. Not too bad, right? The next, so we do sig figs, right? Run according to sig figs. This one. How about these? How are we going to round those? Exactly. Fewest decimals. So actually, it looks like, if you look at C, it looks like we have 3 decimals here, 2 decimals here, and 3 decimal places here. So we're going to have to round according to 2 decimal places. Does that make sense? Okay. The fun comes in with 22 a little bit. So let's see, number A, that's according to sig figs. Number B, sig figs. Now, C, you are both adding and subtracting in the numerator, then you have one last thing to divide it out, right? The order of operations are to do your multiplication first, multiplication to get division first, and then your addition and subtraction. But in this case, you have something, otherwise, you have to resolve your numerator first and your denominator first and then divide it out. Okay, so be careful with that one. And D, it looks like you need to, I would do it stepwise, honestly. I would, like for D, I would do my addition, and then my denominator, do my subtraction and addition, and round according to decimals, and then I would do one last division, okay, to get the right answer. Okay, then these, 23, this will give you some, sometimes students, you guys come to this class with an assortment of backgrounds. Sometimes scientific notation is kind of a, wish you didn't have to do scientific notation. So this really is going to be a good exercise for you to use scientific notation. You can, see me outside of class or that sort of thing. Remember, you have the answers to 23 under doc sharing. That's a thought. Okay. The other thing, though, and actually there's a hint down here at the bottom under 24. Actually, there's a hint, both of them. Anytime you're using the square root, okay, like that, the square root does the same rules as multiplication and division. So, yeah, they look kind of, you know what E just screams to me? If I was doing this one, I would do it once, get an answer. I'd do it a second time to see if my answer agreed with my first answer. It's like bouncing your checkbook and getting the same answer twice. You're like, oh yeah, I got it. It's all good. And you're going to get, if you're like me, like E, you're going to do some nesting of your parentheses. Or if you don't like to nest parentheses, then just do little bites and write down the answer. And then do another bite and write down the answer. If that makes sense. So this is all good. Do you have any questions? So that's due Wednesday too. Okay. That's all I got today. And we're out.